Here we're going to look at basically repeated multiplication on complex numbers. And so repeated multiplication is the same thing as raising a number to a power. Now, there's a famous mathematician, DeMoivre's, who created a theorem to explain how to raise polar complex numbers to a power. Again, this is an advantage of having complex numbers in polar form. Makes multiplication much easier. So repeated multiplication certainly garners the same benefits. So since an exponent is repeated multiplication, we can apply the idea of how to multiply complex numbers, which tells us to add the arguments and multiply the moduli. We just do it many times, okay? So if we look at the complex number z, which let's call r times the cosine of theta plus I sine theta, we can see that the modulus is r, the argument's theta. If we raise this to the nth power, we raise z to the nth power, what that means is we're going to multiply the modulus times itself n times. Right? Because I multiply the moduli, and if this means I'm going to multiply this whole thing n times, so I need to multiply r by itself n times. Which is precisely r to the nth power. And here for my argument, I need to add theta to itself n times. Which is the same thing as n thetas, right? If I take theta plus theta, that's 2 theta because I'm adding 2 thetas. Theta plus theta would be 3 theta. N thetas added together would be n theta. It's that simple. Okay, so let's try this on an example. I've got this complex number 1 plus I need to convert it to polar form and then raise it to this power, 20th power in this case, and I'm going to write my answer two ways, one in polar form and second in rectangular form. Okay, so the first thing I need to do is convert 1 plus I to polar form. So let's go do that. 1 plus I. If I look at a picture of 1 plus I in the complex plane, it looks like this. I go 1 in my real axis and I go 1 in my imaginary axis. So I get this point here. And my theta, since this is, I went 1 right and 1 up, my reference angle is 45 degrees, so my theta is pi over 4. Okay? So theta is pi over 4, and r is going to be the square root of, well, 1 squared is 1 plus another 1 squared is 2, so r is going to be the square root of 2 using the Pythagorean theorem. So now I can see that 1 plus I can be written in polar form as r, which is square root of 2, times the quantity cosine of theta, which is pi over 4, plus I times the sine of pi over 4. So this is the polar form. So now I can come back and I can replace 1 plus I with this. Okay? So I need to take that number and raise that number to the 20th power. I need to multiply this polar complex number times itself 20 times. And so I take my modulus and I multiply it, because you always multiply the moduli. I multiply the square root of 2 by itself 20 times, which is exactly the square root of 2 to the 20th power. And then I'm going to have cosine of, my new argument is going to be pi over 4 plus itself 20 times. So that's 20 times pi over 4, which is, of course, 20 pi over 4s. I suppose we could write it as 20 times, so there's no confusion there. So 20 times pi over 4. That's from adding pi over 4 to itself 20 times, plus I times the sine of the same thing. And then when I simplify this, the square root of 2 to the 20th power is 1024, and 20 times pi over 4 is just 5 pi. And so this is my answer in polar form. When I raise this complex number to the 20th power, I get this complex number. And this is the polar form of the answer. The rectangular form of the answer, I just go and kind of simplify this up a little bit. The cosine of 5 pi is -1. And the sine of 5 pi is 0. So I get I times 0. So that's what I have in the parentheses, -1 plus I times 0. And out here I've got 1024 times that. And then if I distribute my 1024, I get -1024 plus, well, 1024 times 0 is 0, so -1024 plus 0i, or I could just write -1024. So this is my rectangular form of that same number. So when I take this complex number 1 plus I to the 20th power, I actually get the real number, -1024. There is no I component. You can't tell that as easily in polar form, so sometimes it's nice to see the rectangular form so you can understand what the result kind of looks like. Okay? So that is taking a complex number, raising it to a power, leveraging the concept of converting it to polar form first, because then all you have to do is repeatedly multiply the moduli and repeatedly add the argument.